Hello viewers, this is Mix91 and welcome back to these hacking tutorials I've been making. And today, well, instead of continuing with scripting and Pokemon Silver, I thought of doing something different. So the first plan for today, or the plan I had was to tell you something about looping and create that counter script which I uploaded a video of. But well, we'll be doing that eventually, but not today. And for today, we're actually going to start off practicing a totally different thing. So instead of scripting, I'll move on into a thing called assembly. And well, this shouldn't be that bad, because well, if you have been able to keep up this far, it's just a new step ahead, but it's nothing extremely complicated or anything. So well, you've got to focus on what I'm going to tell you today, and you should do it just fine. And I'll also try to do my own very best for recording this, because well, I might forget to say some very important things that will totally confuse you if I don't. So I'll do my best and we'll see how this works out. So for starting out, let's take a look at this picture here. So well, before anything, what assembly is? Well, you know about scripting. How it works is that, well, scripting is a programming language that is, or the scripting we've been doing is using a programming language that is built in those games. Pokemon Gold, Silver, and Crystal all have a similar scripting system to each other. Gold and Silver actually have a totally, or their scripting systems are totally the same. Crystal's is a bit different, but still. They all have a scripting system built in, and well, we've got another programming language behind it, and that programming language is the machine language, the one that the processor uses. And machine language is what we call assembly. And with this assembly, or ASM, you can do pretty much anything the hardware is capable of doing. And well, like I've explained before, we have ROM, RAM, and a processor. And RAM is RAM memory is writable and accessible. So from processor we can both write, so this is write, and well anyway, we can write and access RAM. But from ROM we can only read, because that's read-only memory. So when we process instructions a process code, yeah. We read data inside the ROM, or normally. We read data inside the ROM and store it somewhere in the processor. And here we do some job, and when we need to save something or some calculations or whatever happens inside the processor, we save it here in ROM for further accessing. So from ROM we only read memory, and here we can write whatever the results of the calculations we're doing with the processor are. And that is what ROM is used for. And of course we want to write there so we can put data in use further in the code. So, well, yeah, processor is the does everything that happens in the game, and these are just memories where certain data is written from or read from. And inside a processor we've got a thing called registers. And what these registers are, well, they are small memory slots. And actually they are especially small. They are all, each one of these registers, except for these PC and SP, they are 8-bit long registers. So yeah, they are 1 byte long. So inside each register we can save an 8-bit value or a 1 byte value. And with these registers we do all the counting that happens. And when we need because, well, we can only save a little bit of data inside these registers because they are only 8-bit long. We save most of the data in ROM, and from ROM we bring the data for registers to usage. So it works so that we can't write in the ROM just like that, or we can't do calculations with ROM just like that. First, to do a calculation, we have to bring the value or the address where we want to write something or use or whatever happens. We need to bring that value or address into some register or registers. And with these registers we do the calculations and save the result in the ROM when it needs to be saved. And that's how it works. And here, well, the system we're working with, Gameboy, it has a processor that is very similar to this Z80 processor. So just like described here, we have these registers A, B, C, D, E, H, L, and flag register, which is F register. These are the registers we're using. And just like I said, each one is 8-bit long. They can only save 8-bit data inside them, or 1 byte value, because that is the same thing. And apart from these, we also have program control registers. PC and SP, and yeah, these are 8-bit long registers, and these program control registers are 16-bit long. So in other words, they can save 2-byte values, and these can save 1-byte values. Yeah, program control registers are twice the size of these normal registers: A, B, C, D, E, H, L, and flag register. And still, we also have a thing called index registers and hardware control registers. And I won't be explaining these much at all for now. I might come to it later, but not in this video, or the second one, or the one following this one, but maybe sometime later I might come back to this. But the thing is, we have these registers, and these are the normal registers we use for pretty much all the calculations we can do with this assembly language. And PC and SP, and well, it's also important to know how these two work, especially SP, but PC too. So, well, I'll come back to that soon enough. But this is the general idea. So normally we read data from RAM, save it into some register. Pretty much every time we save the value written in RAM to register A, and this is because A is the special register. It's different from B, C, D, E, H, and L. And we'll come back to this later as well. Why is that? And well, yeah. Here's another picture. So, well, I don't think I'll be explaining much about this either. And the other reason is because, well, I don't know how this works that well, so that's also a case. But well, we've got certain components inside the processor. So this is the processor. We have the place for registers, and those registers, the values can be read from those registers and put into this internal data bus. And from there, we send the values into ALU, and this ALU is a thing called Arithmetic Logical Unit, and it is the thing that knows how to calculate everything inside the processor. So if we, for example, want to make it so that we use the value written in register A and want to add, for example, 20 to that register value, we put the value in A from this latch into ALU, and the value 20 from the other latch, and tell ALU that we want to add them together. And well, this thing knows how to do that. And then it also knows how to Well, yeah, it does that, and it brings the value into this internal data bus, and normally after an operation like that, we would store the result into register A. So that would be a thing called add operation. We want to add 20 into value of A, so we do add operation to put A into ALU and 20 into ALU. It adds them together and stores the value in the register A. And we also got a thing called address buffer, and well, I won't be talking much about how this works because that'd be too complicated for now, and I don't understand it totally either. But well, yeah, we got different registers and can do operations with them, and we also got program control registers. And these how assembly works is that just like the scripting language, we can write code in an understandable format, just like how I described that add operation. We could compile a code such as this one into the ROM, add A, and here we got the value we want to add into A. So this here would be things such as this. With this operation, we can increase the value of register A by 20. A is A plus 20. And this is just one example of how the operations work. And well, yeah, it's kind of difficult. I'm actually not quite sure how I should move on from here. But we can do operations with the registers and store values in them. And as you can see, they can only hold 1 byte values, and that could be a problem because, for example, inside the ROM we've got pointers that are 2 byte values, and we also got some other bigger structures that might require having bigger memory slots for storing data. So out of registers, we can form 16-bit long register pairs. And we've got registers A, B, C, D, E, H, L, and F. And totally we've got 2, 4, 6, 7, and 8 registers. So out of 8 registers, the processor we're working with is able of using these registers also as 4 register pairs. So we've got 4 register pairs, which are AF, BC, DE, and HL. And they can all store 16-bit values or 2-byte values. So if we, for example, said that value of BC was 075A, that would mean that the value of register B is 07 and value of register C is 5A. So both these registers can they can store a byte value in them, because a byte is a 8-bit long structure of ones and zeros. And well, with these register pairs, we can now complete bigger operations, such as if we want to deal with pointers. Pointers are 16-bit values. Because pointers are 2 bytes long, they're 16-bit values. These register pairs can now deal with pointers. And well, I'll be expanding stuff here later as we move on, but for now I'm going to show you how the syntax works. So what kind of operations we've got and such. And just like with scripting, we have codes such as check, poke, give item, face player, and such. And they all translate into bytes. This is 6A. Was this 1F? Probably something like that. And I don't know what this one is. But still, they are all presentations of bytes. So when we use PKSV, we can write code by describing their commands as text, and that is a thing called symbolic presentation. We can, with symbols such as face player, describe that we are writing 6A inside the ROM. And assembly works the exact same way. For example, here we have a symbolic presentation of a command that could be written in hexadecimal if you want it. So add A with N. This is some hexadecimal. This could be written in hexadecimal as 1 byte value. But it can also be written as symbolic form. And the things, or the assembly editors, which I'll be explaining soon and showing how they work, they can write the data as bytes inside the ROM. But we can also, instead of dealing with hexadecimal or binary, we can instead write code in symbols such as add. And like you can see here, we can deal with 16-bit registers with these commands as well, such as HL. That is a 16-bit register, formed with registers H and L, or 16-bit register pair. And A here is just one 8-bit register. It can save a 1 byte value. But yeah, so we can write data with a hex editor or an assembly editor or a binary editor. It doesn't make any difference. But assembly editor gives us the opportunity to translate the hexadecimal or binary code into this symbolic form, such as add instructions. Then we have AND instructions, call instructions, compare instruction. This is a thing called decrement and such. So each assembly instruction, these are called instructions. They're 1 byte long. And just like with scripting, instructions can have parameters. Like you can see here, we have a thing called call instruction. And call instruction works so that call is a 1 byte 1 byte value, and beside call we tell the address where we want to call data from. And this works in the exact same way as call works in scripting. It can call a subroutine. And this here could be written in hexadecimal format as CD, XX, UU, where these two define the address where we want to call data from, or they are a pointer to that address. And call is CD in hexadecimal format. But instead of CD, with an assembly editor, we can write call, which makes much more sense. So each instruction is a 1 byte long value. Here call is a 1 byte long value CD, and it has 2 parameters which define which address it calls data from. And for example, we can also, here's the compare code, CP. It compares A with value N. And what it does, compare A with, let's say, compare A with 0E. And this checks whether the value of A register is 0E. And if it is, it affects, whether or not it is, it affects flag register. So it writes something in register F depending on whether A is 0E or not. So if A is 0E, this checks this. It's an A minus N subtraction. And if A mean -1 is 0, jet flag is set. Okay, and I'm back. You probably heard that it was our dog barking there, and which interrupted the process, so I had to quit recording for now. And I could actually pull off a pretty good joke related to interrupts. We're going to discuss sometime later, but because you don't know about them, I'll just pass. But yeah, so what was I about to say? Yeah, so if A was 0E, so if A minus 0E is 0, so A is 0E, jet flag is set. And inside this flag register, we have different bits. Uh, well, there are more, but there are these 4 bits inside the flag register: Z, N, H, and C. And with the assembly instructions, you can only actually work with Z and C flag. This is 0 flag, and this is carry flag. And in this case, Z flag was set. So we could, for example, check whether A is 0E, and if it is, Z flag is set. And then we could have some operation that check whether Z flag is set or not, such as read Z. And what this thing does, it's return if Z flag is set, and goes back to executing the code that was executed before. Well, if we, for example, if we have this as our subroutine, and A is 0E, then this return tells the processor that we are going to go back. We'll have main routine here, call subroutine. So we call this instruction set from it. It does stuff here if A is not 0E, but if it is 0E, it goes back to the main routine, and here it does stuff. So if here we call this subroutine, and if at this case A is 0E, it checks whether A is 0E and returns back here. And if it's not 0E, it does more stuff, and sometime later with, for example, read code, which is return code, and it doesn't care about flags. It will eventually get back executing code here. And in this case, carry flag. Well, if our A is 0A, that is smaller than 0E, so carry flag was set. If we still do the same thing, so we compare A with 0E. But if A is, for example, 2D, that is bigger than OE, and carry flag was not set, or carry flag was actually reset, it either sets or resets it. So it changes the value of carry flag into 0, and this one changes the value of carry flag into 1. And inside flag register, we have these small memory pieces. Our flag register, just like any other register, it's an 8-bit long value, so it could actually store 8 flags, and each flag can have the value of 0 or 1. And 2 of those flags are, for example, the carry flag and 0 flag. And it also has N flag and H flag, and probably 4 more. Or it has more, but I'm not quite sure what those are. I haven't studied the functions of Gameboy CPU that much, so I would know. But flag register holds the value of all the instructions that occur. And apart from these, it also probably has some other memory slots for handling with things called interruptions and stuff like that. But yeah, this is what this machine language looks like. So we've got these operations you see on the left, and some of these use parameters and some do not. And this actually ain't any different, or it's different, but it's not no more complicated than what we have been dealing with scripting so far. We have a 1 byte long instruction, and with it we either have parameters or don't have parameters. And what we can do with this then? Well, I won't get into that yet, but before this part, I made these small examples, which I'm going to show you now, so you can see how it works. This first one is about load operations, and we've got load operations a little bit below, starting at here. So load in this symbolic language, it's LD. And what it does, it loads the value from the second part into the first part. So if we, for example, want to load the value of register C into register A, we write load A, and this mark here, I'm not sure what it is in English, can't pick it up now. And then we write C here, and that puts the value of register C into register A. And this N here describes what kind of what the second part has to be like. So I'll just refer to this one as the first part and this here as the second part. And the second part can be anything from this. It actually can't be A. You can't load A with the value of A, but you can load A with value of B, C, D, H, A, L, and this here, or these three here, along with this. All of these I'll explain very soon. This here describes just that we can load any value in the register A. But before moving on into this, let's write some own code here. So as examples, we can load register A, so LDA, with 2F. That is, load A and N as 2F. This puts value of 2F into register A. That's what it does. Then we can load the value of A with value of B, and this thing here puts the value of B, register B, into register A. So registers hold a value inside them. That's how it works. And if we, for example, try doing something like this, HL, it's a 16-bit register pair, so it contains 16-bit value. And register A contains an 8-bit value. So you get an error message something like this if you try to write this as an assembly instruction, because this won't work. You can't load an 8-bit register with a 16-bit value, of course. But instead, well, let's think about it this way. We've got this operation here. It puts an 16-bit value into one of these register pairs, BC, DE, HL, or SP. So if we, for example, want to let's load register BBC with the value of 09 DC. So what this thing does, it's the same thing. This is the exact same thing as load B with 09, load C with DC. It loads both two registers with 1-byte values, just like this. We load 09 into B and DC into register C. And now DC, now this was a bad example. Let's just change this to, 4. That's better. So now we load B with 49 and C with DC. And if we wanted to do something like this, load A with BC. As you can see, this was one of the instructions we can do. What this thing does, it loads a value from the address loaded in BC and stores that into register A. Because this has to be as the second part, telling where it loads data, and in the first part we have where the data is stored. So what this does, it loads the value written in the address of register B per BC and stores that into A. And another example, if we want to load HL with D123, this thing here tells that H is D1 and L is 22. Yeah. And let's just say that we have value of 51 in D123 in RAM. So if we now do this kind of operation, after this one we've got value of 51 in register A. So we can use this as a pointer. This HL is a pointer, and if we put it in these marks here, we can tell that we want to load a value of that pointer into A. So we've got pointer or address D123 in HL, and we bring the value loaded in HL, which is D123, into register A, which is now 51. And I've got these examples below, so let's just check them out. I actually wrote this with another computer, so they may not be marked so well sometimes. But here we, as you can see, this is what this does. This do. Loading register D, value of D into B. If we load D with 07, B with 04, B with 07, and here we, with LD, D with B, we bring the value of B into D. And after this one, we've got D register as 07. And here, just like what we've got here, we're loading a value from RAM, straight from RAM, into register A. So instead of here we did it in pieces. We first loaded HL with the RAM address, and then brought the value, loaded in a address loaded in HL into A. It's kind of complicated to say that, but you should probably get the idea. And here we just load the value from a RAM address into register A, and then we transfer that value into register B. And after this one, we've got register B loaded with the value of RAM address D123. And here we do load operations in pieces. First we load D and E with these values, so we've got DE with 2105. Then we load value of E into H and value of D into L, and we've got HL as 0521. As you can see, E was 05, so we load 05 in H, and D was 21, so when we load that into A, L, we've got HL as 0521. Next, we've got this operation here for loading a 16-bit register pair with the 16-bit address. So we load BC with D002. Next we load the value of RAM address C450 into register A, an 8-bit value from this RAM address. And here we load the value of A into the RAM address loaded in register pair BC. And this is how we could, for example, this is how we can bring the value loaded in RAM address C450 into D002. Next, got another example. We load HL with the RAM address, and next we load a value into the RAM address loaded in HL. So where's it here? Is it? It's this one. Put value n into R1, and R1 can be any register besides register F. Normally we're not dealing with F register. That is only written to during some operations, but we can't ourselves affect it with the codings. But as you can see, HL and A are somewhat special. They are mentioned in quite many of these instructions. And here we can, for example, load any value into the address of register pair HL. So here we can, with these kind of commands, we can load value of 35 into RAM address loaded in HL, which is CB30. And if we try to do something, the same thing with register pair DE, we get an error. This command here is... We also get a compilation error here. It can't be done because our assembly language simply doesn't recognize an instruction just as this. We can't load a value into address of DE. We can only, as you can see, register pair HL is the only register pair that can deal with these kind of operations. BC and DE can't, and so can't AF, which is not really used as a register pair at all. But we can do the same thing in 3 pieces, by loading DE with the RAM address, and first loading the value in A register, and then transferring the value of A register into address of DE. Now that works. As you can see, we can do the same thing with register pair AL in 2 instructions, but if we want to use DE, for instance, we need 3 instructions. We need A for taking that value and then bringing that value into our address loaded in DE. And this is how load operations work. Next, we've got some other operations. Increment, decrement, add, subtract, and compare. And increment instructions, they are used for increasing a register value by 1. And you can see that we can increase the value of register A, B, C, D, E, H, L, and once again we can increase the value loaded into address of register pair HL. So if we load DHL with D004 and put inc and HL as this n here, we can increase the value in RAM address D004 by 1. But the other operation here, increment register NN, BC, DE, HL, and SB, if we write load HL with D004 and increment HL, the address will increment, not the value. If we got it in these marks here, with what we've got here, that means that we are dealing with the value, and if we don't have the marks with the 16-bit register, we're dealing with an address. So here we simply actually increment the value of L register from 04 into 05. And here we load A with 1F and increment A, and A becomes 20. And just like here, load HL with D123, increment HL. HL is D124. And we can do the same thing with just incrementing L. And HL is also D124. And here is some notice I've written down. So we can increment value of a register, or increment value of a register pair, or increment value in the address pointed by the register pair, which works only with register pair HL. and not any other register pair, just like B, C, and D, E. And then we've got decrement. And well, before moving on into that, you can see that by incrementing a register, we are modifying the flag register also. And well, if the result of incrementing is 0, jet flag is set. So how could this happen actually? If you think about it, we are only adding 1 into a value. If we add 1 into 1F, we get 20. Add 1 into D1, 23, we got D1, 24. But if we load A with FF and increment A, now A is 0, 0. And why is this? Well, that's because A can store an 8-bit value inside it. And this assembly works so that after FF, or after all the bits are 1, all the bits turn 0. So here we've got A is 1, 1, 1, 1, 1, 1, 1, 1, or 8 bits, or ones. And when we increase that by 1, all the bits turn 0. And when we want to adjust some kind of counter that would actually increase the value even when this happens, we need to check the Z flag. The Z flag every time we're incrementing the register, and if it's set, we actually want to increment some other register or some other RAM address or whatever, but still so that the overall result will still increase, just like we want to. But jet flag is set if result is 0, and it becomes 0 if we are increasing FF. And if we increase FF, the result, in this case A, turns 0, 0. And we have decrement. And just like that, we can also, just like increment, we can do the same operation with the same registers A, B, C, D, E, H, L, and again value loaded in HL. And we can decrement a 16-bit register B, C, D, E, H, L, and SP. And I'll be explaining SP and PC a bit later, but I will explain them soon enough. So, if we load DE with D1 0, and decrement DE twice, we get DOFF. Decrement, so we decrease value by 1. Again, if we wouldn't be decrementing DE, if we only would be decrementing E in this case, then we actually have this one. Because, well, we're not doing anything with D. D still stays as D1, and if we subtract 1 from 0, 0, we get FF. So you can also decrease it to become bigger, like this. But if we decrement a 16-bit register, then this would be D0FF. And next, if we want to load register A with that value, we load A with the value of DO. Value loaded in address DOFF, and we can store it in DO04. And now if we still decrement, or decrement the value of DE, This actually can't be done. Yeah, this can't be done because we can only decrement HL like that. So forget about this. This is a false instruction, it wouldn't compile if we try to compile it with an assembly editor, so we can do that. But yeah, just like with increasing, same thing goes with decreasing or decremented, that kind of stuff. And here we've got add operation. Add also contains the special operation for working with carry flag. But, well, I hardly ever use it, so you don't have to know about it yet either. But we can, for example, add a value into register A and add a 16-bit value into HL. So load A and B with 2 values and add value of B into A, and we have A as 0.5 plus 0.6, which is 0B. And if you load A with value of 13 and HL with D560, we can add the value of HL into A. So now A is 13 plus the value in RAM address D160. And if we want to bring that value in A back into D560, we load the RAM address of HL with A. And these kind of operations are actually quite useful. So we first load A with the value and HL with the RAM address, and then we can modify that RAM address by adding the value of A into it with A. Add A and the RAM address here, and then we load the value of A back into it. And assembly allows a lot of handy tricks, and even if you don't understand how to code properly with it, you can already achieve a lot of stuff just by knowing the basic instructions. And as you can see, add operation also can set the 0 flag if the result is 0. So if we load A with 80, add A with A, that would be 0, 0. And chet flag is set. And subtract n from A. Again, we can subtract any register and the value of register HL, a value loaded in register HL, and any other value as well, like that 51, okay, showed in that example. And chet flag is set if result is 0, and C flag is set if no borrow. And this was explained in the compare path, I think. Yeah, set if no borrow, so set if A is smaller than N. So if we subtract something bigger than A from it, then carry flag is set. And here we have B with 0E and load A with 17. We subtract B from A and A becomes 09. And then the other way around, load B with 17 and A with 0E. we subtract b from a, you could calculate it like this. Because now the result goes under 0, 0. It pops back into FF. And it works like this. You could add 100 to that, what we got here, and you get the result of the instruction. So with this one we've got F7 loaded in register A. We subtract 17 from 0E. And here I actually got a bit, a little bit, a more difficult instruction set. So first we load A with the value of RAM address D9 AB. Load HL with RAM address D005. Next we subtract 8A from, we subtract the value of HL from A, and like I said here with the no borrow thing, if carry flag is set if A is now smaller than the value of HL. So if originally the value of RAM address D9 AB was smaller than the value of RAM address D005, then carry flag is set. And if carry flag is set, we actually jump to another routine with relative jump gr command. And I'll explain the relative jump and jump commands quite soon, but this is how it works. We can check whether carry flag is set, and if it is, if carry flag is set, we jump to a new routine. And if carry flag is not set, that means in this case that A has the value of HL or something bigger. And in that case, we could bring the value of A into D9AB, which would do this. So we would subtract the value of D005 from it after this instruction set. And RET is a return code, like I explained before. And if carry flag was set, we do something else. We, for example, load the value of A. We load A with value of 0, 0 and put that into D9AB. So this could be a code for subtracting something from the value of this RAM address. And if the subtraction goes below 0, 0, it automatically writes 0, 0 in there. And if it doesn't go below 0, 0, we have something else in here that was smaller than before. And we could be using an assembly script such as this that we call from an original script data, and next we could bring the value of D9AB into RAM, which is I'm now talking about the scripting engine. So the RAM is D173, which we can compare with the if commands. And now we could check whether if RAM is if true command, we would check that if true would check. Well, yeah. Well, it's hard to explain that, but I think you get the idea. This is how it works. And here we got compare A with value of n. And this, well, it doesn't really need much of an explanation. we can compare two values with each other by keeping the original value of a as the same. So after this operation, a is still 0, 5, and 0 flag was reset. And we can load HL with RAM address and bring that value into A, and this would be stupid, but next we could, for example, compare whether A has the same value as what's written in the RAM address loaded in register bear HL. And that is because we just loaded that there. So in this case, 0 flag is set because A truly has that value in it. So you can also do something stupid like this with the assembly, but it makes no sense to do anything like that. Yeah. This is pretty much about these instructions. I'll still explain these call, jump and related jump, and end, and or, and exclusive or commands, and next time we'll be doing some experimenting with this. So, call command is used for calling a subroutine. And what it does, it pushes the address of the next instruction on the stack and then jumps into the address that it calls. And this explanation, it makes a lot of sense, but it can be really difficult to understand, especially if you are not used to programming and things such as stack pointer and program counter. And those two are these program control registers. And call command is dealing with both of them. So if we, for example, use call 5500, it's used to call subroutine, and when we end that subroutine with return command, RET, it comes back to executing code after this command here. And as parameter for call command, we have a ROM address where we want to call data from. And that is actually put into register PC. PC is program counter. And what it tells is where the next instruction to be executed is located. So each time, well, in this one, we transfer these values as the value of program counter, so that the processor knows that the next instruction is to be executed in this address where program counter points to. And normally, or every time an instruction is executed, program counter is incremented by the amount of times that instruction requires. For instance, compare code, compare A with 0, 5. This takes 2 bytes. So when this command is executed, or after it's executed, program counter is incremented twice, so that it knows that the next instruction to be executed it follows this instruction. Because if it wasn't incremented twice or at all, it would be executing the same command again. Yeah. So when we compare A with 0, 5, program counter is incremented twice because this instruction takes 2 bytes. But yeah, along with a call command, we can adjust flag, jet flag, or carry flag, and call address n if following condition is true. Condition CC. This can be nchet, chet, nc, or c. And you can see that these mean that call a subroutine if chet flag is reset, if chet flag is set, if carry flag is reset, or if carry flag is set. So, in this case, we call a routine from ROM address, which is ROM bank program counter. A ROM bank in this ROM address. We call data from if chet flag has the value of 1, so it is set. And that way program counter is changed into 7203. And here we have a subtract command. We subtract value of B from A, and if carry flag was reset during that subtraction, we call a subroutine from the current ROM bank, and the pointer would be 4A58 in big Indian format, actually. So if our ROM bank starts at C000, we are calling with this subroutine data at CA58. And then we've got jump command. This simply changes the value of program counter into the value following it, telling the processor where the next command is to be executed at. Jump 62A7 changes the program counter into 62A7. 16-bit register, 16-bit value. And jump also has a same kind of case as call, not chet, jet, not carry flag, or jet flag reset, jet flag set, carry flag reset, carry flag set. Decrement A, if 0 flag was reset, go to this address. And what this could be referring to would be if A wasn't 0, 1, then jump here. And if A was 0, 1, continue doing stuff after this command. So continues doing stuff here if A wasn't 0, 1. No, if A was 0, 1, we do stuff here, and if A wasn't 0, 1, then 0 flag was reset during this operation, and program counter is changed into 6840. And we can also jump into address contained in HL. So if we want to load HL with 58B2, we can jump onto it. And this also won't make much sense written like this, because it takes one more instruction related to this, but we never use this instruction in a case such as this one. Instead, we do a lot of stuff here, which actually change the value of HL depending on several cases, and then we jump onto it. And that's actually when this is useful. And JR is a relative jump, and it works the exact same way as jump code, except for it being able to change the current value of program counter by 80 into any sides at maximum. So this can jump anywhere in the current ROM bank, and this can only jump a little bit ahead or a little bit backwards, because it uses only one parameter instead of two, which are used as the pointer. Can jump at maximum 80 bytes away from the current address, and works in both directions. And ASM editors support writing GR command and its parameters as an address, but actually it's saved as the address is saved as 1 byte, telling how far ahead or backwards we're jumping. So here, JRN, add n to the current address and jump to it. So add n into the value of program counter. That's how it works. JROD, jump to address PC plus OD. JR88, E8, jump to address PC plus E8 minus 0x100. And it's probably GR values bigger than 80 as the parameter tell that we're going to jump backwards. If they are smaller than 80, we're jumping ahead. But yeah, you can write the GR code just like you write jump. So if we are currently executing code at ROM address like this one, there we've got this is totally okay to write it like this with an assembly editor, because this new address is in the range of 40. This plus it is in the range of yeah. And assembly editors can compile it into the ROM correctly. And some might be nitpicking to me about this, because this range is not totally true. It's not 80 to both sides from the current address, because program counter is already incremented twice after this. So because this command takes 2 bytes, GR and 1 byte signed immediate value, we are actually currently in ROM address 134502 after the command, and from here we can jump 0x80 bytes into both directions if we want to be well, yeah. I can't find the right word, but that's how it goes. And last but not least, we're actually going to deal with the probably most useful, well, maybe not the most useful, but extremely useful commands as well. We have you can think of bytes as well, in mathematical logic we have AND, OR, and exclusive OR operations. And these are most used for comparing two sets with each other. And if we AND two sets, the result is a new set that contains the values those two sets share in common. And if we use OR operation with two sets, the result are all the values of those two sets. And exclusive OR is a subtraction operation of OR and AND. And with bytes, it's really no different. So with AND operations, if we've got when we are ANDing two bytes with one another, we're actually comparing their bits. So here I load A with the value of 36, and that is this 8-bit value in binary. And now next I load B with value of 15, which is this kind of a binary number. And if I AND them together, I get a new value that has only the bits these two share in common. So here you can see that A has 1 but B has 0, though this is 0. Here we have, they both have this bit as 1, so it becomes 1 in the result. So here, so does here. So it becomes 1 here. But here we have 1, 0, 0 and 1, so those two become 0 zeros. So AND 1 B gives 14 as the byte value, and that is stored in the first register, A. And not very surprisingly, we are ANDing something with A and bring the result in A. And again, B, C, D, E, H, L, and value of HL, and any 1-byte value are the possible things we can be ANDing with. Yeah. This is how it works. Load A with E4, load B with 0, 0. If we AND A with B, we get 0, 0. So these are all special cases I've documented here. If we AND with 0, 0, the result is 0, 0, of course, because if you AND anything with 0, the result is 0. ANDing two 0, 0s together gives 0. ANDing 1 and 0 together gives 0. And ANDing two 1s gives 1. If we load A with 7B and D with FF, and load AND A with D, we got the original value of A. Which probably makes sense, because all of these are 1s, so we are actually ANDing. Well, you can see how it works here. If you AND a register with another register with the value of FF, all the bits that were originally 1 are 1 in the result. And here I am actually adding something with 0F, which is now A9. And A9 is 1, 0, 1, 0, 1, 0, 0, 1. And OF is a value that has the 4 highest bits as zeros and the 4 lowest bits as ones. And if you AND A with C, you get a value that has the lowest bits as 1 that were 1 before. So the highest bits are... This actually, what it does, it changes the highest bit, 4 highest bits into zeros. So these two become zeros here. And the result is 0, 9. And the same thing with F0. In F0 we've got the 4 highest bits as 1 and the lowest bits as 0. And this here actually is 1. Kinda missed it. But it works. Works as the final result. Now that we ended with F0, only the highest 4 bits have the original value and the lowest 4 bits are turned into zeros. And the result is A0. And you can see that if you add them together, these two together, you get the original value of A, which was A9. So, end A with 0F returns the values of the lowest bits into A. And if you end with F0, you get the values of the highest 4 bits. And we also have another common instruction called AND A with A. And if you think about it, no matter what we've got in A, for instance this one, if we AND it with itself, we get the original value, which probably makes sense. So value of A isn't changed when you AND A with A. But what is useful then? Each time you AND 2 registers, carry flag is reset, as you can see here. And if you AND A with N, carry flag is reset. And because AND A with A doesn't affect the value of A, it can be used as reset carry flag instruction. Yeah. And I actually happen to teach you a word of Finnish while at it, if you paid attention. That was because. But yeah, so the game makers pretty much use or only use AND A with A operation for resetting the carry flag, because it's good for that. It can achieve carry flag resettion in 1 byte. The 1 byte instruction. There are many other ways you could reset the carry flag as well. For instance, this one where we and if we want to AND A with FF, carry flag is reset and A has the original value. And we can also reset carry flag by this kind of thing. Set carry flag SCF operation. And next we complement carry flag, which gives the complement of the carry flag value. So if carry flag, first we set it, and then we take its complement and reset it. And that takes 2 bytes and 2 instructions. But AND A with A is faster. It can be executed faster, as it's only a 1 operation code, and it also saves space. Next, we've got OR instructions. So when we OR 2 bits that are zeros, the result is 0, and if either one or both are ones, the result is 1. And here we load A and B with values and OR them. As you can see, both of them have the first bit 0, so in result we have it as 0. Next, A has the second highest bit as 1, although B has it as 0, the result is 1. The third highest, B has as 1, A has as 0, and it will be 1, the result. The next bit, both have as 1, the result is 1. And this is how it goes. And this is how, after this command, we've got 7A loaded in A. Next one, load A with DB and load B with 05 and OR them together. And you can see that this bit here was set and the result is DF. Next, load A with F0, load B with 0F. 1 1 1 1 0 0 0 0 and 0 0 0 0 1 1 1 1, and the value is FF. All bits are set. So OR A with F0 sets the 4 highest bits of A, which probably makes sense. And if we OR A with 0F, we can set the 4 lowest bits of A, as you can see here. They are all unset, but we can set them by ORing with 0F. And OR doesn't have any this special function like AND has this AND A with A operation. But OR can be quite useful at times as well. And then we have exclusive OR command. And let's just ignore this for a while. Exclusive OR works so that when both values are 0, the result is 0. When either one of them is 1, result is 1. And when both are 1, result is 0. And here I'm first using AND operation for AND load A with 58 and B with F3. And when both are 1, the result is 1. And these two here happen to be 1 in both, and the result is 50. And if we OR them together, we get FB. And when we XOR them, we get AB, which is FB minus 50. So let's just think about this. AND sets, when we AND two values that are 1 together, we get 1. And in other cases, we get 0. And in OR operation, when we OR two values together, of which either one is 1, we get 1. And when both are 1, we get 1. And XOR is actually a subtraction of these two, which, well, yeah, it's a subtraction operation. If we XOR two values together, we're actually subtracting what their AND value is from their OR value. OR A with B is FB, and A with B is 50, and exclusive OR A with B is AB, which is FB minus 50. Yeah. XOR is a subtraction operation of A and B. And here we've got a special case. We load A with 63 and load that value into B, so they both have the same value. And when we XOR the same values together, we get 0, 0. Because if you think about it, in each case, both values are either 0 or both of them are 1s. And both those, when you XOR two zeros together, you get 0, and when you XOR two 1s, you get 0. So result is 0, 0, no matter what the value of A originally was. If you XOR it with itself, the result is always 0, 0. So yeah, just like AND operation, also XOR offers special use behind it. And here if we check about it, logical exclusive OR with register A, leaving a result in A, and again we can use the same registers for XOR instruction. And carry flag is always reset during this, but 0 flag is set. But just like with any other operation that can have the value of 0. Jet flag is set if the result is 0, and if it's not, jet flag is reset. And if we XOR a value with itself, we always get 0, 0, and jet flag is set. So, XOR A with A can be used to set the 0 flag, because XORing with itself always gives the result of 0, 0. And this is often used in the games as well. Just like AND A with A, that can be used to universally reset the carry flag and doesn't affect register A in any way. XOR can be used to universally set the 0 flag. But the problem with it is that it also changes the value of A into 0, 0. But that's what it does. And next, let's just think about it, how this XOR actually works. Because it's a subtraction operation of OR and AND. So we might be able to write it, or we could write it in with these ASM instructions using OR and AND operations. And I've done this for you. So here we got the XOR, and as you can see, it takes quite a lot of instructions. And I have succeeded to build it in 8 instructions. So XOR A with B. First, we've got some random values in A and B. For instance, these 58 and F3. So first, we load 58 into register E, because we need to store the value of A for further usage. And then we OR A with B. And this operation stores FB into register A. And next we store that FB into register D for further usage. And next we bring the original value of A from register E into register A. So now A has 58 in it. And then we AND that value with F3, and A turns 50. And next I put that 50 into register B with load B with A instruction. And next we bring the result of the OR operation that was loaded into D back to A. And now we have, in A we've got the result of OR operation, which is FB. And in B we have the result of AND operation, like down here, which is 50. And then we subtract B from A. And finally, A has the value of XOR A with B. So this is how you could build it in assembly language with 8 instructions. Yeah. That was not very useful, but I wanted to show you how it works, and that's how it goes. Because it's a subtraction operation, you can do it using subtract instruction and it's using OR and AND as part of it, so we need OR and AND for building the code. OR and subtract along with some other memory slots as E and D in this code. We can build a XOR operation for two values that were in A and B registers. And that's pretty much all for today. And well, next time we'll be going back to scripting and using assembly as part of scripting. And after it, I'll be explaining a program counter and what this is. It's a thing called stack pointer, more properly, and what stack actually is. And after that, probably some other assembly coding and how to use it as help. Probably a bit about debugging, which you don't have to know anything about right now either, and more stuff related to that. But that's all for now, and hope you enjoyed and actually understood what I was trying to prove. So, well, yeah, I'll input this document as downloadable in the how to say it, not signature, but well, you can find it attached to that video in the not comment section, but whatever it's called in English. But yeah, see you next time. That's all about it.